talk is actually about non-Hermitian quantum mechanical systems, which you read from the abstract. The thing is like, so this is the outline of the talk. Like in traditional, I have been part of Vikiran talks at the start, and the classical tradition is like something like this: the starting everybody is very attentive, in the middle everybody is big, and last. So I will try to not make that happen. Like I will try to make it as interactive, and I have maximally bypass all the mathematical parts so everybody. So let's. So these are the papers which I will be reviewing in this talk. Like the first of all is the seminal paper by Carl Bender, who sort of starts analytically to approach these non-Hermitian Hamiltonians. Then this is the Nobel Prize winning paper by David Thouless, the quantization of particle transport. Third, I will talk about scheme modes and topology in non-Hermitian system. Fourth, these are localization transition. I will smoothly touch about it. And fifth is very important. It's about the exceptional points. Another is like exceptional points can give rise to topology and everything. I will talk about what I mean by topology in some brief sense. And a very important thing is later on is that this generalized Reynolds zone, this non-Hermitian classification. And another one is like in the symmetry and the topology that are interconnected to non-Hermitian physics. And last of all, like this is a very famous optics paper that how this exceptional point topology can give rise to. They have seen something very interesting, which I am not so much. I mean, I am not an expert in optics, but there are some very deep connections with exceptional point. So, yeah. So this is actually the world map that we are in. Like there was quantum spin-Hall effect and topological insulators in the world. There was topological insulators, but this dragon actually destroyed all of this and built up all of the fun. Although people are still writing papers on this, and now the search has been on the non-Hermitian topological states in this shape. So this big dragon is like the physicist, and the search is actually ongoing. So the question mark is because what I believe the map is not already complete. Like I believe that there will be an unification. It's only my personal belief between this Hermitian and non-Hermitian system, which will be classified in near future. And the conclusive part is that physicists are dragons. And another thing, you can see a word like topological insulators, which are like you can induce light into a system and you can invent topology. So yesterday I found a very beautiful animation that what is actually going on in like some 15 seconds. So here is the animation. Suppose this is a material you induce light, and there are circular bulk electrons are there, and around the edge there are propagating modes around the system actually. So this is actually light induced topology and here is topological insulator. So caution, I see there are many postdocs and PhD here. So the research isn't known to experts, but I guess it is not entirely known to most of the people. I'll try to give my little understanding. And there is a chance that this expert might visit their downstairs. So I will try not to make that happen. And let's begin. So this is a 2×2 Hamiltonian. As you can see, if alpha is not equals to 1, this is a non-Hermitian matrix or a Hamiltonian. And you can see that if you got the eigenvalues or can compute the eigenvalues, it's generally complex. Now, if it will be complex if alpha is like something like -1 or I or n. If alpha is -1, then you can see it's just plus minus square root of I. And if anything like that, I mean, in general in non-Hermitian system you get complex value, but there are scenarios where you can actually have real spectrum also. But the most interesting part is if you compute the eigenvectors of corresponding these two eigenvalues, you will get two non-orthogonal states, which look something like this. And actually, this gives rise to some very beautiful implications, like this state, what I call as left state, and what I call as right state. There, because there are things like if you have a Hamiltonian. Suppose if you write an eigenvalue equation H psi equals to E psi, and the dagger of this by taking the Hermitian conjugate of this thing, you will see that suppose you as this Hermitian regime, what happens is as these two states are orthogonal, it will cancel from both of the sides and it will equals to star. So that means that in Hermitian system that the eigenvalues are always there, as you know. But in the non-Hermitian system, as H is not equals to H dagger, the eigenstate that will diagonalize this eigenvalue equation will not be the eigenstate which will diagonalize this eigenvalue equation. So we name it like this is the right eigenvector and this is the left eigenvector. And these two states are orthogonal, and here the problem comes. Like if you when you solve the particle in a box here. So the problem comes when you solve a particle in a box. If you just encounter the states, like suppose this is the particle in a box, and there are states n equals to 1, n equals to 2, n equals to 3. If you take the eigen function of psi 1, psi 2, and psi 3, if you do an integration psi star psi 1, it will also always give you 1. But if you integrate over psi 2 on psi 1, it will give you 0 because the states are orthogonal. And it is important, if the states are not orthogonal, fermions cannot occupy it. And if there is some finite overlap between two states, we cannot say that the particle truly is entirely in this position and there is no probability transfer to the other state. If the states are not completely orthogonal and finite overlap. So this is a very important implication of non-Hermitian system, and this 2 plus 2 Hamiltonian is showing. The obvious question comes that if you want to calculate any average like ODAC and you should calculate the average, in Hermitian regime is very easy. You calculate the eigenstate and you take an average. But in non-Hermitian system, as you have two sets of eigenbases, there are questions like which of the eigenbases will you take? Will you take psi r to the both side? Will you take psi n to the both side? Or will you take psi r and psi n? And the thing is like as psi r and psi l are not orthogonal, what we do, we have to impose the bi-orthonormality condition, like we have to brute forcefully make them orthogonal by transforming these two different eigenvectors, psi r prime and psi r n. And when you take expectation in those bases, you call them as the bi-orthonormal framework. And thereas these two states are orthogonal to each other, then you can define every average values and everything quite easily. So this is a very important implication I want to make.
Can you again explain that bi-orthonormal states?
Yeah, so I will repeat.
Bi-orthonormal.
Yeah. So the thing is like when you take an average in Hermitian system, it's very easy to do this. But now as you have two sets of eigenbases, which of the bases you will take while measuring the problem? It's a confusion, right? So what people do, they map in such a way that where psi r prime is actually psi r divided by psi l. Now you take the inner product between those and you see it will go give us 1. Because you divided it by the norm of the two things. But we have to also give a completeness criteria. This has to also satisfy, and there will be some implications towards this. So this is actually called the bi-orthonormal framework, where you have now two states which are completely orthogonal each other, and now you can take the probability. Although there are papers like where they have taken like psi r to both sides and they mention this like OR and OL and ORA by taking different states and see how it is.
So here you have just normalized your two eigenvalues.
Yes, but you said that we used to do this in the same basis, right? In the Hermitian case also we used to normalize the eigenvalue.
Yeah, normalizing is fine, but how will you get orthonormality just by normalizing? Normality is fine, but the orthogonal condition there is.
Yeah, it's not sufficient. Then you have to do a basis, right?
Completeness is still not orthogonality, right?
At least you have to subtract the component along psi 1, right? Then only you can get.
No, that means a projection. Like when you subtract a basis vector, that means a projection. But I am telling that if you have two sets of eigenvectors, psi r and psi n, these two, and I have transformed it like this, that doesn't ensure an orthonormality, but you can see that here it will serve the purpose. But the thing is, like, they have to form a complete set of bases. Otherwise, how will you span the entire Hilbert space? So these two conditions are sufficient to form the set of bases. Like whenever you diagonalize the Hermitian Hamiltonian, what you get? You solve the eigenvalue equation. You get, suppose H is 20 plus 20. So there will be 20 eigenvalues corresponding to it. Specifically, if you take a general case where the levels are not degenerate, you will get 20 eigenvalues corresponding to it. And corresponding to each eigenvalue, you will get 20 eigenvalues. Right? And you can normalize it by just taking eigenvalues between those and dividing it by this. But they are forming a complete set of bases. The point is, as there are two distinct set of basis vectors, because what is diagonalizing this eigenvalue problem is not diagonalizing this, the problem is.
In the Hermitian case,
Yeah.
all the eigenvectors will be orthogonal. That's the problem
Yeah.
of Hermitian matrix.
Yeah.
In a non-Hermitian case, we haven't checked orthogonality.
Yeah, you don't have. That's why we have to measure any properties. We have to brute force this bi-orthonormal framework, which is not orthonormal framework. And we have to brute force it.
Savvy brute force that
You use a Brownsman process to make them all.
Yeah. So Brownsman is a way because only this thing will not hold in this regime, but you have to have satisfied the company. Yeah, your question.
Sir, are you saying that Child prime and Charal prime are orthonormal?
You can make it.
But now we have divided by that norm, so they are not orthonormal. Like the inner product should be 0 for to be orthonormal. It's 1.
No. I mean, yeah. So there are two basis sets like this psi r and psi n. Yeah. So I made the mistake. Psi r and psi r is psi n. Yeah. Now they will actually be provided the completeness holds. Provided the completeness holds. So this is not a general framework, in general framework, but it will hold to actually measure the bi-orthonormality condition. If you have some doubt, I will talk. So another thing is like the exceptional point. So you take this Hamiltonian, this supposed to Hamiltonian. It's clearly it's not Hermitian, right? If you compute the eigenvalue problem, you see there is only one eigenvalue which is lambda equals to 1, and which has an algebraic multiplicity of 2. If you compute the eigenvector of the corresponding Hamiltonian, you will see this eigenvector has a geometric multiplicity of the eigenspaces 2 because there is only one corresponding eigenvalue. Now there is a problem. Problem doesn't have a full basis of eigenstate. So what I mean by full basis of eigenstate is the problem. Suppose you have a n cross n vector space. Now to write any operator or explicitly write any operator in this vector space, you have to span the Hilbert space and you need to have an entire set of bases, n number of bases. Now between, if two of them, at least two of them are collapsing, then you don't have the freedom to span out the entire Hilbert space because you don't have the entire number of linearly independent bases vector. So that's why we call this matrix defective matrix, and this is very important point. Like you can see that the lambda equals to 1 level is degenerate. There are two eigenvalues. So in Hermitian system also you will say like what's the problem? We have degenerate eigenvalues in our real world problems, right? But the eigenvectors corresponding to those eigenvalues, they are not equal. Not equal in the sense they are not coalesced. But here, as you see the corresponding 1 and 0 bases, is actually having a geometric multiplicity of 2, it causes a problem. So around the exceptional point is really difficult to diagonalize the problem. And
Like what do you mean by exactly by algebraic multiplicity?
yeah, algebraic multiplicity means your lambda minus 1 whole square is equals to 0. So
Achha,
1 comma 1. Like don't have any geometry degree of freedom to entirely span the area. Like suppose you have 2 cross 2 problem, you have 2 eigenvectors. You can have the eigenvectors by expanding like 2 arrows. But here you have only 1 because there are no other eigenvectors. So the entire problem comes there. Like you have an n cross n, you have n arrows, and now 2 of them are merging together. Now you don't have those entirely linearly independent set of bases, so that you cannot express new operators. Yeah, geometric means geometry in the eigenspace, not in real space, obviously. In the eigenspace, like in the space where the vector is in actually, the eigenspace is used.
So how will you complete this?
Yeah, this is a problem. There is a way to handle it. I mean, I am not talking it like, yeah. So how to compute it is actually mentioned in this book by very nice. It's a perturbation theory for linear operator. So what actually they do, like at exceptional point there is a problem, right? So what they do, they go to very close amount by perturbing the system by some very complicated way, and they actually diagonalize the problem around the exceptional point and get some idea that what is going on. At exceptional point is very difficult. We obviously cannot write a theory, right? So this book is written by Toshio Kato, and this is the preface to the first edition, and it is written that this book will be useful to students as well as to mature scientists, both in mathematics and the physical sciences, who would like to be reading this. And the next thing is like this exceptional point is actually very powerful experimental crystals. Like there are fermions in photonic crystals, and there are like enhanced sensitivity against small perturbations shown in optical microcavities, and these are all coming from this exceptional point. So this exceptional point photonics is actually very powerful. Like I haven't read this paper, but there are great number of experimental implications of this exceptional point. The main idea of this non-Hermitian system is like, so when you are treating a quantum mechanical system, what you assume, like when you go study QM1 or QM2, you set to assume that there are no interaction of the quantum mechanical system outside your Hilbert space of interest. But when you solve a real life quantum simulation problem, there will be losses, there will be interaction. And to give an effective framework, these non-Hermitian systems are very useful. So actually, so these are a basic summary that when you have H is equals to H dagger, so it's a closed system. As the matrix is Hermitian, your time evolution is unitary and it's conserved probability. So as you have seen previously, it doesn't conserve the norm. So that's why in non-Hermitian system, it's an open system. The time evolution is non-unitary. It does not conserve energy and it is lossy. And another implication is, like when you deal about the topological aspects of Hermitian or non-Hermitian system, this is another thing. Like I told that Hermitian Hamiltonian usually give you real eigenvalues, and the non-Hermitian Hamiltonian usually give you complex eigenvalues. But there are reasons to it, and the topological aspects is like in Hermitian systems there are actually 10 symmetric classes, and in non-Hermitian system, due to this type of problem, the symmetry classes expanded up to 38. So this symmetry classes means it's on the type of thing like parity symmetry, time reversal symmetry, sublattice symmetry, p-tau together, and due to this type of problem, it extends up to 38 symmetry classes. So handling it a bit difficult. So in context of physics, like since Dirac, we considered that energy is actually real and all the Hamiltonians are Hermitian, but in the non-Hermitian framework, when you diagonalize the non-Hermitian Hamiltonian, you get to have some imaginary eigenvalues. But it is not the case that always comes up, because there is a class of non-Hermitian Hamiltonians which don't give me Bender actually shows if you have this PT symmetric transition, I will talk about what PT symmetry is. It has a real spectrum, entirely real spectrum, even the matrix is non-Hermitian, and it has some huge implication. So what is PT symmetry? So there is a report actually written about a painting drawn in the wall of a Lithuanian restaurant, and people believe and thought this would be as PT symmetry. So there are different consequences of as I'm showing this picture. But yeah, this picture is actually I have taken from Hilbert's so it's a I don't want to take it. Yeah. So what is this? So now you say that this is the Lorentz group formalism, and the space-time distance between 2 points, if you perform any coordinate transformation, is always preserved. So the parity and the time reversal symmetry means if you have an x, y, z, t, parity means you just take the spatial reflection and you transform it from minus x, minus y, minus z. And time reversal means you just take the t to minus t. So now this is a picture where the parity symmetry, you can see this is the mirror reflection, right? So this is a very nice picture, also taken from Bender's slide. And Bender is actually the seminal person who actually talked about this PT symmetry quantum theory quite rigorously and in the context of physics. So inside the physics, he has also some very good mathematical example that how you can think of this non-Hermitian system. So he thought that suppose you have a closed box with gate. Now what do I mean by that? Suppose you have a box, non-interacting box, and it has some energy or particles leveled by A already inside, and you are gaining something which is coming from outside and it is leveled by this I. Now it don't have to be an imaginary quantity associated with it, but consider it for a moment now. Later I will see that this I is not necessary. You can put or you may not put, it doesn't matter actually. And now what you do, so this can be energy and particles and anything. So it's something is coming out. So it is the non-Hermitian system, right? Something is interacting from the outside of your closed system of interest. And in the second part, what you will see that there are two non-interacting boxes. Something is coming in on the first box and something is coming out of the second box. And you can write the combined Hamiltonian of the system by A plus IB as B is coming in and A minus IB, the B is coming out. Now what he did, he joined this by a coupling by a phi, and it has some strength. You can think of that this whole as a coupling strength of G. So now you see this is a very important transformation what he made. Now you see due to this coupling strength, energy particles from box 1 can go inside box B, and then it came out. So this is a very beautiful Hamiltonian written in of this system, and this Hamiltonian is not Hermitian, but it is PT symmetric. How? Another thing, like due to this introduction of this coupling strength, this box can have reached equilibrium condition, like whatever is coming inside in one rate is completely going outside in another rate, and it can sort of equilibrate the system. Also, if you solve the eigenvalue equation for this problem, you will see the energy eigenvalues look something like this. If A, G and B are real, you will see the energy spectrum is real only if mod G is greater than mod B. So you see at mod G equals to mod B there is a transition. Before that the energy values are complex, and after that the energies are real. So you are actually in the non-Hermitian framework, but due to this PT transition that you are going from mod G less than mod B to mod G greater than mod B, there is a PT transition, and it gives rise to real spectrum, and these are the experimental papers that this PT symmetric laser and this PT symmetric photonic lattices are recently coming out. So these are all nature items. So when I now consider about topology, I want to show you a trick like when you talk about three-dimensional rotation, a topology matters a lot. Suppose I have this book and you do a pi rotation around this axis, pi rotation, another pi rotation. It doesn't configure anything. If you do a pi rotation and 2 pi rotation for 2 times, that means a 4 pi rotation, it actually again transforms to the same thing. But if you do this with an object which actually keeps track of the memory that what has been done to it, like a belt, you may have seen this experiment. It's called the Dirac's belt. Like what you will do, that suppose you have a belt and suppose these two faces are facing towards you, you give a pi rotation and you give another pi rotation, you will see there are 2 nodes, right? So somehow the book doesn't keep track the rotational transformation that we have performed, but here these 2 nodes are actually keeping track of it. Now the 2 pi rotation and the 4 pi rotation are trivial for the book, but it's not trivial for this belt. Like if I give another 2 pi rotation, a pi, another pi, you will see these 2 endpoints are always facing towards you, but there are 4 nodes now. But believe it or not, this 4 pi rotation is topologically trivial. What it means that I haven't actually rotated this belt. What I can simply do by facing, I am not spinning the 2 ends, by actually facing these 2 around you. If I just interchange it, it doesn't mean any rotation is happening. So it's a very weird kind of thing, and this problem has a very beautiful solution given by Dirac, that this SO3 group, that 3-dimensional rotation groups, truly depends on the whatever topology we are applying. So if I again transform it like this, 4 nodes are still. So that means there are no true rotation is happening. However, if you do a 2 pi rotation, suppose these 2 faces are facing to you, 1 node, 2 nodes, and you perform the same trick. I am not spinning the 2 ends. You cannot get rid of the 2 pi rotation. So what that means that this 2 pi rotation and the 4 pi rotation are topologically non-trivial. The 2 pi rotation is topologically non-trivial. You are asking something? Yeah. Are topologically non-trivial. But when you keep doing this exercise with your book, it's fairly simple, right? You do a pi rotation, you do a 2 pi rotation, it comes down this. If you do a pi rotation, you do 2 pi rotation, 4 pi, it comes down. So you cannot differentiate this.
What I'm asking is like, in what way are this book and the belt topologically different? Like in what sense?
Yeah. So to actually, when you see the solution of this problem, that why it is happening, what you do, you place the belt on the board. You at every space-time point, you draw an axis, 3-dimensional axis. When you are talking about the book, it's not actually preserving what rotation I actually doing. Like when I am talking about that you gave a pi rotation and a 2 pi rotation, you see the endpoints is behaving like a book because it is facing you. Although, but this strip-like topology is actually keeping track over the memory that whatever rotation I actually perform. And these nodes are actually equivalent to actually on the band topology in the condensed matter system, where you also cannot get rid out of the nodes. So this 2 pi rotation, when there are 2 nodes here, are topologically non-trivial.
Isn't it more like local and global transformation?
Yeah,
Because
something like that. So actually, when you see the solution, what it tells like that if you define any vector on this SO3R, you can map it on a surface of a sphere, and then from there you can give a very nice analogy. So the trick of this belt is called Dirac belt trick, and there are very beautiful solutions available on the internet that how these rotations are actually happening on the belt.
When you were flipping the book, you were taking the book as a system and then you were doing.
Yeah, there is no way to keep track of the memory.
Yeah, but then here you are only flipping one end of it. You are
Yeah.
not taking the whole system and flipping it.
Yeah, that's
So even for the book, if you flip it.
Yeah, then it will be like this. Yes, you are right. You are right. So as in now, these 2 points are like placing like a book, right? Like what you are telling that if I take this 1 and 2, then it will do whatever the book is now exactly doing. But if you keep track of the memory, now why this is important, I will tell about. That's why these nodes are very important. That somehow the memory, that whatever transformation you do with the belt is actually keeping track of this is actually very important. So another way to give sense of topology is like suppose you have this belt and a ball is actually rotating around the belt. Now if you just flip one side of it, keep it as to a Mobius strip, right? And now you have to do a 2 pi rotation to be on the other side of the sphere. You can do and think about it. So these two are obviously topologically distinct. So in classical world also this type of topology is manifest and very beautiful. Now a few days ago there was a talk on integer quantum perspective given, right? So there he talked about 2D realization of integer quantum perspective, that you have a finite sample, there are electrons on the bulk and there are electrons on the edge because of the finite size system, and you apply a giant magnetic field at t equals to 0. You will see that the bulk electrons keeps on rotating because and they cannot conduct any electricity. However, if you locally manifest on the edges, there are skipping modes, and this circle cannot be completed, and the electrons on the edge is actually on the skipping modes, and it actually provides an unitary direction of current around the edges. So this is actually topologically non-trivial. Why? Because if you stretch it, these two sides, or you perturb it with any disorder, what happens to these skipping modes is actually topologically intact. So that means it's topologically protected. So this skipping mode and the disorder is actually equivalent to a cup, like where there is one hole. Like you all see this transformation. Like suppose you have a torus like this, and from there you can make a cup with one hole. Like these two are topologically equivalent. So to drastically change, and the number of hole G is actually one here. The number of hole, the genus, is actually the topological invariant that keeps on distinct. Suppose if you have a tori like this, where there are two holes, where G is 2, to drastically change this topology, you have to cut it. You have to do a drastic transformation. There cannot be any smooth transition to actually change the number from G to 2 to G1. So that means these two things are topologically distinct. And what is happening here is actually related to this smooth adiabatic transformation, that whenever you stretches these two sides or add any perturbation, due to this topological protection, that you actually can smoothly transient anything, but you cannot change this topology. Like here also G is equals to 1. In 2 of the cases, it actually gives rise to this topological protection. Now, in physics, like this is the 2D topological insulator example. Now, in 3D, in 1D, before that, I also have to give you some beautiful things about, like when you apply this giant magnetic field, if you give it like in terms of flux, and if you compute in a square lattice, and you compute the eigenvalues with the number of quantas of flux you are sending towards it, you will see such beautiful patterns are emerging out of it. And this is the very beautiful name. It's called the Hofstadter butterfly. So this butterfly-like structure actually emerged, and this is actually experimentally verified in whole atom experiments, that you can actually get such beautiful butterfly-like structures coming out of it. So it's actually, you see the power of quantum mechanics, that it actually gives us something so very beautiful that beyond the classical regime of physics. So in one topological system, the first very simple toy model that was shown in coming from a polyacyclic chain, where you can see there are 2 carbon atoms, and if you map it to a 1D system, so it's like a 1D nanowire, where I'm coming from 2D to 1D. So what are the implications of this protected mode, what you have seen in 2D in 1D? As there is nothing to propagate, all the topological modes, if it is topologically non-trivial, will be at the edges. So we are very much interested about the edges. So what happens in this Schur-Schrieffer-Hiller model? So it's the simplest 1D model you can think of, and there are hopping. So what I mean by hopping, the electron hops from this side to this side with the hopping term V, and this side to this side with the hopping term W. Now this is the two-side unit cell. So when you solve the problem, you take these to be a unit cell, and then you solve the problem, which gives rise to a 2-by model problem. And this is something the Hamiltonians ignore this. And this model is Hermitian, because in the Hermitian regime there is no type of losses from here. But what happens if you plot it for n equals to 4 unit cells, the matrix is 8 cross 8. This is OPC. OPC means open boundary condition and PDC means periodic boundary condition. Periodic boundary condition means suppose you have this 1D chain. What you do, you merge these two sides together. So this is a periodic boundary configuration. That's why you see at the ends, at the off-diagonal end points, there are a hopping term W in the periodic boundary condition. Just because you have merged these two ends with a hopping term W. This side with the black side, with the W. That's why this W term is coming, which is not present in terms of the OBC Hamiltonian. So the thing is, like, if you plot the mod chi square, like where will be the maximum probability of the electron, if you have an 80 side model, like a chain of 80 sides, you will see it will localize around the edges. Now this means this edge localization is somewhat topologically non-trivial. See, there is no bulk localization as such, and all the particles orbiting the probabilities are localized around the edges. Now in Hermitian regime, what I have shown, I mean, it has been shown that you cannot move these edges from one side to other without doing any adiabatic evolution. Now what I mean by adiabatic evolution, like here I have shown, like you have a torus, and from there you have make a cup, but the G is unchanged. And how do you make the cup? By taking G unchanged, you do some smooth transformation. Now if you do some smooth transformation of these hopping parameters, you can actually pump this one state out of the another state, and this state will come to this side. So there will be a spontaneous pumping of charges along this polyacetylene chain if you do a adiabatic evolution, but any distinct change in the parameter, like you take V1, W2, V3, W1, you will not see this continuously propagate. However, in the non-Hermitian system, it is not like this. In this paper, in collaboration which I have written with Abhishek, who is the batch 16, and Dr. Pusha is a professor from SBS, and SD Mohan is a professor from Michigan State, we have found something very interesting in terms of static pumping. What we have found in the Rice-Pilley model means you have the same model, but on the on side you have some delta and minus delta potential. These delta are actually modulating the density profiles of the mod chi square. But actually, if you introduce a non-hermiticity parameter, like previously it was V and W, right? Now what you do, you take that from A to B, when there is a hopping, there is a V minus gamma, and from B to A, when the electron hops, the strength is V plus gamma. So this gamma is actually the non-Hermitian parameter. If you put gamma to 0, it will reduce to the Hermitian regime. And if you write the Hamiltonian and plot the mod chi square, you see something very interesting. You see all the bulk states are not localized around the two edges, and it actually pushed all the bulk modes towards the edges. Now this is very interesting. This is truly a behavior of the non-Hermitian system, where there are no end modes, and even if there are end modes, all the bulk modes are 0, and everything is pushed over one side of the chain. And these modes are called the spin modes. I will talk in detail about
what plus delta and minus delta.
Yeah, those are for the density modulation. So you can take it as a mass term, like it breaks that time symmetry. Break the time.
I didn't understand. So how will you break down symmetry?
Oh, okay. So then you have to write the time reversal operator, right? If you do this, so you will see H2. So this is a truly time reversal operator, right? So if you introduce this delta term, it will not obey this. So it actually breaks one of the symmetry of the problem. So basically you may think that due to this modulation it's happening, but it is not. If you put delta equals to 0 and still plot the spectrum with the finite gamma, you will see still it's happening.
And physically, what does it mean?
Physically mean there are two different potentials about it. I will show an animation that one.
What could be the reason for example, earlier what I thought that gamma is coming because of the differential potential of that 2
gamma
points.
is actually hopping anisotropy. So you can think of that there are baths attached to it, where the particles are actually going. You think about the box problem. Something is coming inside the box. If something looks similar like this, right? The V plus gamma and V minus gamma. So what is very important that you can actually think of that. You see, in every unit cell, it will be V plus gamma. It will be V plus gamma. So this gamma is actually like pushing all the modes towards one of the and there will be a scarcity of modes due to the V minus gamma.
What I was saying that gamma is coming because of the delta. If the delta is set to 0.
No, gamma is a free parameter what you have set actually to carry out so the thing is, this is not the only way to make it non-Hermitian. If you put gamma equals to 0 and delta to be I delta minus I delta minus I delta, introduce some complex potential, the model is still non-Hermitian. So it will be a completely different model to analyze, where each side there are some complex potentials. So,
like what could be the reason for this anisotropy?
So hopping anisotropy is like what I told, that there are some baths attached to it, and some particles are interacting with the S side of the electron and the B side of the electron. And an effective framework is, so this is a toy model, right? This is not an actual material as such. So this gamma is actually coming from those baths and actually going around from those baths. So it's coming, it's going.
And the source of potential also is same?
Yeah.
Baths, the same baths.
Some baths attached to it, or some masters.
Okay.
Yeah.
Are the multiple points on the graph multiple values of gamma?
What? Pi?
Multiple points on the graph.
Multiple spines.
Point.
Points on the graph. Yeah.
Are there multiple values of gamma?
No. This is you diagonalize the Hamiltonian for 40 sides. You plot all the eigenvectors. You will see for a finite value of gamma, this is the mode that everything is actually pushed to one side.
There are a lot of different colored points.
Color points, because there will be lot of different vectors, right? Due to each point, like A, B, A, B, A, B, A, B, A, B.
So the pink color is the ground state, and I think the blue color is the highest state.
No, I just plotted 2 or 3, like, okay. So I will be showing a spectrum plot after this. Now, if there are suppose 20 distinct eigenvalues, there will be 20 distinct eigenvectors, right? So that's also
Which one is the ground state among these curves?
So ground state is, okay, so ground state for a complex, how do you define complex number to be small or big? You cannot, right? These are yeah, so in PT symmetry, like this problem is actually violating the PT symmetry due to the introduction at certain point. So there are complex eigenvalues. So defining a ground state is a bit of difficulty, technical difficulty, but you can when you are in the PT symmetric regime where everything is zero.
So yeah, how are you comparing this probability at side index?
Yeah.
How are you comparing this probability at side index to topology? To topology.
There is no topology in this picture, right? There is no topology. It's just the bulk modes I have plotted, and you see the bulk modes actually. So if it is a topologically non-trivial state, this mod psi square will hit 1 because the entire particle will be in one of the edges. So you see it's quite low, right? 0.20 or something like this. So these are all bulk modes of the system. But what I am trying to say, you see, at the bulk there is nothing, but everything is actually pushed around one of the edges. So it is a non-block behavior, like it's not exponentially. Well, you can see that this is exponentially decaying through the edges. So this is a non-block behavior of the eigenmode that is happening here. So in Hermitian system, if you plot the bulk modes, you will see there are localizations here. It's evenly distributed, not just entirely pushed to one of the sides.
Like you just started explaining in the start that when you have non-Hermitian Hamiltonian, then you will have the two non-orthogonal eigenstates to it.
Yes.
So right now, what are you plotting? Like
Yeah.
when you mean
This is psi L.
This is psi
L left, because everything is pushed to the left, right? V plus gamma is. This is psi L.
Okay, so we are basically plotting psi.
Yeah, you can plot a psi R, but yeah, I think this was psi. I mean, this is the side index, right? So 0 to L I have numbered, so this should be psi R, and instead of arrow direction to this one, it should be arrow this one. Yeah.
Okay.
So then it's psi R. Everything is localized on the right side of this.
So if it's not psi L, then it will be just 0.
And this is actually the OBC Hamiltonian for n equals to 3. You see, this V plus gamma and V minus gamma, and if you take gamma to be 0 and take an Hermitian conjugate of this matrix, you will see that this is a Hermitian, right? This V will flip W, W will flip V will flip W. But due to this plus gamma and minus gamma, the non-Hermitian terms is actually arising. And if you take a Hermitian conjugate of this matrix, it will not be equal to right. So this gamma parameter is actually, but in terms of adiabatic evolution, what I have shown and I have told that there are two localized edge modes at the two ends of the system, right? Something like this. And I have told that without any smooth deformation, you cannot transpose these states to one of the other side. But in the non-Hermitian system, what we have shown, so you see, as we increase gamma, you see one of the side edge modes is actually getting reduced and it merges with the Dirac. So this is actually very interesting, and we have not defined any adiabatic evolution in this case. We are just transforming the gamma, and you see one of the edge modes is getting reduced and merging with the other edge mode, while the other edge mode keeps on fixing where it is. So these actually correspond to a very important message that in fact in non-Hermitian regime, in a static non-Hermitian model, you can see the pumping, and you see the pumping direction is from the left to right because the VR is greater than VL. V plus gamma is actually greater than V minus gamma. So the edge mode is actually getting delocalized and is actually merging with the right. So what we have found, we found many different things, but this is one of the key aspects that even in non-Hermitian case, you can actually transform these edge modes to one point to other. Now, importantly note, these are two edge modes. This is not the bulk modes I have shown you earlier. Now, in sense of skin modes, what I have shown you earlier, it's very simple to see that all the skin modes, if I have a hopping anisotropy in this side, everything will be localized in this side, and if I give the hopping anisotropy to that side, everything will be localized to that side. But the edge mode transference, edge state transference is very non-trivial.
This gamma that you are varying, is it changing sign in the variation or?
No. So it's just the mathematics actually keeps on tracking like this. So it's going from 0 to 2 and 2 to 0.
Maya,
What is not static?
Yeah.
What is not static? Like,
What is?
not static. You said pumping in the static mode.
Static means you are not time evolving any system. Like this V, W and everything, these are all like 0.2, 0.3, something like that. So you are not doing any adiabatic transformation to those, you are just changing the gamma from 0.0 to 2.
So pumping in general sense happens in some adiabatic.
Yeah, there is some adiabatic transformation. I will be coming back to this.
Yeah, like why have you have only considered this non-Hermitian parameter for the U thing, like the inter-cell hopping? What about the hopping between the two
Your two units, you can introduce it, but to define, like if you see, so you are telling that this W is from A to B. You can, but then okay, there is a very famous paper regarding this that actually there can be some suppose two such Rice-Milling chain, and you can actually add this to W hopping like W plus delta and W minus delta, and actually can be this model can be mapped to a effective 1D model. So I don't have the essence of this paper, but it can be done. You are right, completely right. But you see, the essence of W is a bit. If you see, if you make this W plus, if you make gamma 0 and W plus delta and W minus delta, you still get a non-Hermitian matrix, right? Because when you take a transform, it can be done.
There in the last animation you shifted the psi to psi r. What's this?
Yeah, so you just change it. There should be some typo in the direction of the hopping, right? Whenever the direction of the anisotropy, everything will be localized at that direction.
In that animation just different. After
No, these two are not skin modes. These two are actually the edge modes. Only two edge modes.
by what are they represented by?
What are
How do we represent?
Yeah, so in the next one it will be get clear. So this is actually a spectrum in the OBC chain. Now this edge modes is actually these two red points, and all the other energies are the skin modes. So the first plot what I have shown are the eigenvectors plot of these modes only, not these. And in the animation what I have shown the eigenvector plot for these two modes. That's why there are two peaks and these two different modes. But the interesting point is, as you smoothly transform gamma from 0.8 to 1.01 or 1.25, you see something very interesting happen. At gamma 1.01, you see two of the modes is actually getting merged. And you remember the exceptional point that I have been told when two eigenvalues will collapse. So this is actually the exceptional point that is arising by transforming gamma. If you do a close observation, it looks something like this. So you see these 2 points are actually merging. Like if you do a very fine precise computation like 1.01024, it will see that it completely gets merged to one another. Now to see this actually happening in very fast. So these 2 exceptional points, so this is the way it's happening. See, the edge modes are still there, but the scale modes are coming towards one another. They form the exceptional point and they disappear. So after you see, after a certain point, after a certain value of gamma, there are no edge modes. So it's sort of a topological transitions. Like previously for gamma 0.8, you have a topologically non-trivial edge mode. After the formation of exceptional point, they both merge out, and now there is no edge mode. So that means you are gone from a topologically non-trivial state to a topologically trivial state, and this is a topological phase transition in the second case while changing the gamma.
That means earlier we already had that edge modes,
yeah,
but all the bulk modes were localized towards the edges.
The other cases, when you changing this gamma, these 2 modes are approaching towards each other, form these exceptional points, and then they merge out, and there are no edge modes now in the real energy.
So for the scaling of modes, we took the eigenvectors corresponding to the
energy to the butterfly level structure, and for the animation, I have taken eigenvectors for these 2 points.
This energy is a between.
So now the very important thing, adiabaticity. So what I mean by adiabatic evolution? So adiabaticity means that your Hamiltonian, the eigenstate of the Hamiltonian will not change drastically if you give a perturbation that is acting on slowly enough and there is a gap between the system. So to demonstrate it, so this is a quantum harmonic oscillator. There are 2 atoms and there is a spin coupled to it, and this is the potential, right? This is the potential for a harmonic oscillator, right? Now, what we will do, if this tends to 0, now what you are doing, you are varying the k. So that's why it's like closing in. But however, if this change with time is very slow, and if it tends to 0, you see at the end where the inclination is very low, the system is almost at this instantaneous stage. Like whenever you have a k of t plus delta t, and if it is approximately equals to kt, like there is not much change in the higher orders, what happens, this psi t plus delta t will approximately of psi t. Now this adiabatic, this is a very faint example of what is happening. To do a more proper mathematical treatment, what you have to see that why adiabaticity keeps tracking everything. Because suppose you have a psi of, you want to compute a psi of t at any time t, what you have to do, now this tau is actually the time ordering operator. Now if you solve this, and you know this is not this is e power a matrix. So if you do a Dyson perturbation, there will be terms like h of t1 integral, and then h of t1, h of t2. Now when you are doing this process very slowly, the Hamiltonian at time t1 and the Hamiltonian at time t2 can commute. So that is the main reason why this adiabaticity is very important. So you see at the last, when there is very little change, the eigenvalue, the ground state energy of the quantum harmonic oscillator changes a very little amount of time. So this key feature actually what it leads to the
This is the ground state or is it the second state?
Yeah.
This is the ground state. And this property that remains in the instantaneous, I guess it is true only for the ground state.
No, it is until and unless the driving parameter is maintaining a gap. Now in quantum harmonic oscillator everything is gap, right? There are distinct energy levels like n plus half h cut omega, so there is sufficient gap. So my animation was actually disrupted by a question, but this actually leads to the very important 2016 Nobel Prize in Physics, which is given to Thouless, one half to the Thouless and the other half to the Halden and Kosterlitz, due to the theoretical discovery of topological phase transition. And this is the Nobel Prize winning paper which I was talking at the very beginning, quantization of particle transport. Kosterlitz and Thouless also wrote a paper, so Kosterlitz is at the postdoc of Thouless, and they have shown a topological phase transition. And you see, remember the very first slide, not very first slide, in the between I have told that you need a large magnetic field towards. Halden actually showed you can actually have those topological edge modes without this large magnetic field, and he got the Nobel Prize due to this by introducing an complex exterior stable. So I will not talk about in detail in this. So the thing is like this paper is very important to whatever thing I am doing. So whatever Thouless proposed that a topological charge pumping is actually pumping charges from one side to others due to a periodic and adiabatic modulation of Hamiltonian parameters. So previously what you have shown that the Hamiltonian parameters are V, W and delta. So if you introduce a V of t like 1 plus cos omega t, W of t as 1 and delta is equals to sin omega t. If you plot a spectrum of in the parameter space V minus W and delta, what will you get? V minus W
Cos
delta. Now if you take this omega to be tends to 0 and we do the process very slowly, this will actually, what will happen, you see the one state will now slowly propagate to the other state. And how it's doing? It's doing by this this particle current operand. Now this C, which is actually integrating over a period of the generally the this inside is actually the Petty curvature, but it is written in 1 plus 1D formalism. So this C is actually your order parameter while doing a topological phase transition. If the C is 0, that means you are in a topologically trivial regime because there is no particle transport. And if C is 1, you will see that around a single cycle from 0 to t, one particle will transfer from one edge to the other. So this C number is very important and it's called the Chern number. But in 1D, in this 1 plus 1D formalism, we will call a pump just around a single adiabatic cycle. So
this pumping only changes the parameter, right?
By changing only the parameters of the system, not putting an external bias. So this is actually very important.
Then how are we exactly controlling the parameters?
In optical lattices, you can actually tune this by using laser potentials.
But it is again some external bias.
Yeah, but it is not a bias. So
Achha.
if you so you will not apply any voltage towards the end and giving an external bias, and it's very non-trivial because see, whenever this cos is having a peak up, the sine is actually getting a peak down. So it's not like you are pushing everything towards one another. It's something a mixture of both that actually transferring the charges. Now in classical pump, what will happen if you have a particle in one side and if there is a pump is going around this, you will see after a certain amount of time this particle will start transporting towards it and it filled up the another side. But this is not exactly what is happening when you are driving to the parameter, but this is an analog that what is happening. So this is actually what is happening. When you are completing a loop in the parameter space, this animation is not absolutely correct. You will see these states. The edge state is actually moving from one side to other through this very complicated mechanism where it is truly non-trivial because one is going up, one is going down, and you are transferring the charges from one side to the other.
The green and yellow are the delta and omega gamma parameters. What are this green and yellow signify?
Yeah, so this delta, which are corresponding to each side, it is some sine omega t, right? So it's actually module delta and minus delta, so it actually module delta the energy profile, but not in a trivial way, it's a non-trivial way. So this thing actually gives rise to phase transition. Now, if you are varying the gamma in such a way that you are going from C0 to C1, that means there is a topological transition and you transported a quantized number of charge to from one side to other. So this is actually topological phase transition. You are going from a topologically non-trivial phase to a topologically trivial phase or vice versa, and this is called a topological invariant. For higher dimensional models called the Chern number, and you see, and this actually is completely equivalent to the number of poles in a spectrum. So just give you so this actually gives rise to a very important concept of the Hermitian system. If you picked up any topology paper on topology, you will see they have absolutely computed the bulk boundary correspondence and established the bulk boundary correspondence by computing the Chern number. So what actually happens, this Bailey curvature or the particle current operator you are actually calculating in the bulk, in the K. K is the momentum scale, because if you have a periodic boundary condition, you have a translationally invariant system. It doesn't matter, right? So momentum is a very good quantum number there. And you are calculating something in between, a quantity in between, but it can predict that if this integration gives rise to +1 or -1, you will see if you have a OPC, there are 8 states at the end. There are 8 states at the end. So this is a bulk boundary correspondence that you are computing a parameter in the periodic boundary condition and which gives rise to the information what will happen in the open boundary condition, and this is called a bulk boundary correspondence. Boundary is at the boundary, and every paper in topological system mainly you will see that this is actually a daily routine and it is something called parampara pratishthan anushasan. However, standard non-Hermitian system usually break this bulk boundary correspondence. Why? Because you see, when you are plotting the bulk modes, it's not in the bulk. Everything is pushed to one of the ends. Now, what is happening in the boundaries is not dependent on itself on the boundary modes. The bulk modes are also getting localized. So, due to this problem, the standard non-Hermitian system breaks the conventional bulk boundary correspondence. And people introduced a non-block bulk boundary correspondence in the system. How? They have mentioned a non-Hermitian topological invariant integrating over generalized Brillouin. Now, what do you mean by generalized Brillouin? Now, whenever it's plotting the spectrum, you will see that the energies have some imaginary components, also some real components. But in Hermitian system, we only have this. So the Brillouin zone is the K zone. The K space is completely defined. Now, as soon as we have some imaginary component, what is the meaning of Brillouin zone? So that's why what we have to do, we have to add K tilde, which actually takes care of this imaginary part which is appearing in the Brillouin zone by some imaginary component which has some mathematical structure I have not mentioned. But then you have to integrate over dk tilde to actually get all the topological Chern number or any computation by get C actually equals to plus or minus 1 by integrating over the dk tilde. So this dk tilde is called what a generalized Brillouin zone. At gamma tends to 0, this non-Hermitian system becomes Hermitian. You will see this k tilde will also become k. So it is actually a sort of like a function when there is a non-Hermitian parameter gamma, but at gamma tends to 0, it's Hermitian. So by analyzing a non-Hermitian system, it's sort of like it's a general structure. By just putting gamma equals to 0, you get to the Hermitian picture. And all of these messes, like all this, and this is one of the case why there are 38 symmetry classes that I have told before, because dealing with this non-block bulk boundary correspondence is very difficult, and the entire mess is because the non-Hermitian scheme. This big stand up.
Bhaiya, what is beta?
Yeah, so I don't want, I told that I don't want to get this mathematical complexity. So the beta is, so when you are considering a bulk boundary correspondence, your Brillouin structure is looking something like this. So e power ik is cos k plus I sin k. So if you plot it, the real part of z and imaginary part of z, it will give a complete circle, unit circle, right? But if you have some imaginary part here, you will see this thing will get shifted or not get shifted. So previously when you were computing in the Hermitian regime, you are actually integrating over this entire loop. So this is obviously a complex integral because many curvature can be complex. So, but whenever it gets slightly distorted, and you will see such pictures in non-Hermitian papers, you have to define a path and then integrate over it, and due to the correction of this part, what inside the loop. This beta is actually, in our case, v plus gamma and v minus gamma square root of v. And also there is an n factor because we also shown there is a system size dependency on it, which I don't want to talk because it's a bit of a theoretical clash between.
What does non-block mean?
Non-block means the usual block bulk boundary correspondence is broken, right? So people call it non-block.
So we are taking non-periodic.
No, it's not nothing about period, it's just a name. Like it's not the conventional BBC, it's NBBC. So it's just a name. In 2018, there is a two Chinese guy actually gave this name.
So, but the block here doesn't mean block function. That you
so
this block function for very phase.
Yeah, so this dk is actually on the periodic boundary condition where the k is actually your momentum in the BBC, right? But here this k delta is not actually in the. I mean, you see there is an imaginary part associated with it. So it's a bit difficult to tell what exactly it is. So that's why people call it a generalized Brillouin zone. Like you are integrating over a generalized Brillouin zone, and then in the entire formalism, they compute the Chern number or in any topological invariant in general, they call it and establishing the bulk boundary correspondence by non-block bulk boundary correspondence. It's just a name.
And wave function also is modified because of
Yes.
Because
So when you compute the Berry curvature, you will take the psi r, psi l from there, and it has to be orthonormal in the bi-orthonormal framework. So these are bi-orthonormal topological invariants. So let's understand non-Hermitian skin effect a bit. So this is the system, right? It's a non-Hermitian system. The hopping is t plus gamma and t minus gamma. I change the notation, and gamma is non-zero. And you see all the bulk modes is actually getting localized at the edges. So if you plot it for any number of system size, doesn't matter how many system size you take, all the bulk modes will get corresponding to one of the sides, and this actually gives rise to a non-block boundary behavior that there is nothing in the bulk and everything is localized at the edge, and this type of transferring, this type of states transferring is called a non-Hermitian skin effect or non-Hermitian skin pumping. It's sort of like a pumping where the bulk mode is pumped out to one of the edges of the system. So this is where I end my talk, and this is challenges that I had. That you see, what I dealt was it's like a simple toy model, right? There is no connection to real material. So what we need to do is do a systematic and extensive many-body analysis of the non-Hermitian models, where there is a topological phase transition in the picture, and active formulations to calculate the open Chern number. Now the open Chern number, what do I mean by that? What we have proposed that these all are calculated in the PBC, right? Where k is a good quantum number. But as there is a system size dependent transition in non-Hermitian case, people are trying to define an open boundary condition Chern number, where they will talk about projectors and everything, which is not yet still defined, and people believe that this open boundary Chern number is actually very much useful in case of particularly of non-Hermitian topology, not the usual block definition. And third is obviously application to the real materials beyond simple toy models like what we did, like in the Kagome or the And fourth is the system size dependent phase transition. Now, what usually happens in non-Hermitian system, if you have a non-Hermitian system and if you have plotted the edge nodes for n equals to 300, you will see that the edges are actually localized, there are nothing in the bulk and there is other edge. If you plot it for n equals to 50, you will see the same behavior. If you see the other parameters, if you plot it for n equals to 20, you see the same behavior. Because system size is actually invariant for a Hermitian system. But if you change the system size for a non-Hermitian system, you will see due to this non-block behavior, in some cases there are edges, in some cases there are not. So in Hermitian system, it's actually non-Hermitian system.